Good afternoon, everyone. Thank you for joining us once again for our final day of monitoring coral bleaching using remote sensing. So far in the first 2 days, we've been looking at certain principles or the fundamentals of monitoring coral health using Earth observation data. We have seen human impacts and effects on coral reefs. We have looked at certain data portals, also like the Copernicus Marine Service, and certain tools like Dunia, EO Africa. Today, we will be continuing with our training, and we will start off by looking at temperature-derived indices for reef resilience monitoring. That would be done by Dr. Marie Smith. Then we would look at setting up the Dunia sandbox and an introduction to Jupyter notebooks. From there, we'll go through certain examples using the Jupyter notebook, an example code, which we'll be using in the Dunia sandbox. And then we'll go through some question and answer sessions and troubleshooting throughout the day to find out how everything is working for everybody. It's going to be a very interactive session today. So I'd urge all of you to give us your attention and also pay attention to the particular instructions being given so that we can work smoothly based on the platforms that we'll be using today. So Dr. Marie Smith will be kicking off the first presentation, which will be focusing on temperature-derived indices for reef monitoring. Dr. Smith, are you there?
Hello.
Can you hear
me? I can.
Yes. Yes. So if you can just share your screen. Okay.
Okay, you can see that, you can hear me.
Yes. 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 We can hear you and we can see it. So you can go ahead.
Thank you very much. Thank you for the kind introduction. Welcome back, everybody. So today we're going to use all of the background knowledge that we received during the earlier parts of the week, and we're going to actually start applying the information with some remote sensing data. So as we've heard during the week, there are a variety of different factors that could cause coral bleaching. Now, this can include things like overexposure to sunlight, extreme low tides exposing corals to air. A lot of it might be related to runoff or pollution causing higher nutrients or higher sediment load in the water. But definitely the most important or the most pervasive threat is the change or the increase in sea surface temperature. So that is why we tend to focus on monitoring efforts in terms of the environmental monitoring on the sea surface temperature of the ocean. So why do we focus on using remote sensing? So it is important to note that it's very important to understand your region of the ocean where your coral reefs do occur. So it is possible to measure your environment through simpler methods, for instance, using thermometers. You can apply thermistor change. You could do measurements from small boats, from ships. You could use more complicated things like buoys or moorings, Argo floats. And it's important to have your in-situ information collections to understand how the ocean works. Unfortunately, in-situ data collection can be very expensive. It's ship time, all these instrumentation, they are expensive. And a lot of the time you're only able to cover a very small area in space, or also only covering a snapshot in time. So when it comes to monitoring an entire reef system or an entire coastline of data, you might find that it is a lot easier to use remote sensing data. So this is where the satellites come in. There is remote sensing techniques can help you to kind of fill in the gaps where you don't have the data, or fill in the gaps in areas where data collection is not possible. So basically it provides you with global coverage because it's routinely collected on a daily basis. So yeah, you can fill in the gaps where your information is not available. So let's just take a little bit of a view of how satellites work. So most of the energy that comes to the Earth comes from the sun, and this comes to the Earth in the form of short wavelength electromagnetic radiation in the UV, or the ultraviolet, and the visible range. And this is also why our eyes were designed to see in the visible range and see different colors, because that is where most of the sun's energy actually comes to the Earth. This is then interacting with the atmosphere, with the Earth, with the ocean, and then gets re-emitted back into the atmosphere, back out to space in longer wavelengths, such as the infrared and microwave wavelengths. Now, it's very important to note that all the radiation that comes to the Earth is influenced by the atmosphere, where it can be scattered or reflected or absorbed. And basically what this means is that there's certain sections of the electromagnetic spectrum where the light cannot actually penetrate, or where the electromagnetic energy cannot actually penetrate. Now, these are known as the atmospheric windows. So this is the areas where the light can be either fully or partially transmitted through the atmosphere. And this is also the areas where the satellite sensors are programmed to operate. So, for instance, optical sensors that operate in the thermal infrared tend to measure sea surface temperature. Now, because thermal infrared energy is also naturally emitted by the Earth or by the ocean, it can be detected at day or night, as long as there's enough energy or a large amount of energy to be recorded by a sensor. So most of the environmental satellites that orbit the Earth are either near polar orbiting or low Earth orbit satellites. So this means that they go around the planet close to the poles, and they measure the planet while the planet is rotating beneath it. This happens when these types of satellites are orbiting at an altitude of less than 1,000 kilometers. It's also important to note that they measure the electromagnetic radiation over the Earth in strips or swaths, depending on their field of view and depending on their mission. So you might find that satellite sensors that need to look at very small features, for instance, on land, if they've got a very small spectral resolution, they might take longer to measure the entire Earth. Whereas for the ocean, a lot of the times the swaths are a lot bigger, so that you can get more frequent measurements of the Earth. Okay, so let's take a little bit of a step back and look at how these satellite information are generally used for coral reef monitoring. Now, NOAA Coral Reef Watch is kind of like the gold standard of coral reef monitoring. NOAA is the United States National Oceanic and Atmospheric Administration. So you might have heard of NASA. So NASA is, for instance, the space and the science-driven missions, whereas NOAA is more the operations-driven organization. So NASA tends to put the satellite sensor missions up into the sky, and then NOAA would use and apply the information for decision-making that the satellites provide. NOAA Coral Reef Watch was specifically established in the year 2000, and they have been developing products and methods that help to predict, observe, and alert users to the threats of coral reef. So we tend to follow the methodology that's been developed by Coral Reef Watch, but they tend to use specific satellites and a specific climatology to create their products, whereas instead we are going to be using the products from the Copernicus Marine Services, and we're going to be using climatologies that we created from our side. So we spoke about the Austere data product earlier in the week. This is the operational sea surface temperature and ice analysis product, which provides a very similar sea surface temperature product to what NOAA would be using. It's a product from the Copernicus Marine Services that's updated daily, and it's also a level 4 product, which means it's been spatially and temporally interpolated so that there aren't any data gaps. So whereas the NOAA products tend to focus only on satellite sensors from generally, they focus more on American or US missions. The Austere product incorporates most missions that are out there. So it's very important to note that the life expectancy of any environmental satellite might only be between about 6 to 10 years. But for operational implementation and long-term monitoring of the planet, it's very important that there are different missions that have similar sensor characteristics that overlap in time and space, so that we can have as complete a science quality long-term climate record as possible. So in this case, the Austere data product makes use of many different satellite products. So they have lots of infrared satellites data, and you can see these, the ones that listed here, are covering different time periods. But luckily they have similar characteristics, so it is possible to create a climate record from them. They also make use of microwave satellite data. This is very helpful for filling in the gaps in space and time. And then they also use in situ sea surface temperature data from ships drifting and moored buoys. And this is in order to create for any biases in the satellite data. Okay, so let's look at what type of information we want from reef resilience monitoring. So I've broken this down in very simple terms. So first of all, we want to know, what is the ocean temperature today? So what are the environmental conditions that the corals are facing on this specific day in time? On the other hand, we also want to know, how does today's conditions compare to an historical average? So is today's conditions cooler than average, warmer than average, and how much warmer than average? And another very important thing is, Karen has mentioned this earlier, that we look at the degree heating weeks, and this is because corals are not threatened, how do you say it? Corals are dependent on the accumulation of heat stress, basically. So you want to know, what has the temperature been over the past few weeks? How much warmer has it been than usual over the past few weeks? And what is the accumulated heat stress that the corals have been facing over the past few weeks? So in order to do this, we obviously need the observed temperature, so basically just the satellite temperature that you have for a specific day. But it's also important to have a climatology, or a long-term condition for a specific time period or a specific place. So when it comes to climatologies, we tend to start off with, for instance, we might have like a couple of years worth of daily sea surface temperature data. So this is just an example of how we're creating the climatologies for the processing that we're going to be doing today. So for instance, if you're looking at about 20 years, you might have about 7,000 or more time steps of daily data. So if you're looking at a satellite data set, you would have a data cube of longitude, latitude, and then time in days. Okay. So that's your first step where you start off with. Next up, we tend to use the monthly climatologies. So in this sense, we're going to calculate the monthly mean over a given period. So for that 20 years, we're going to calculate, for instance, the mean of the period between the 1st of January 2024 and the 31st of January 2024. And we're going to do that for each of the months in the entire 20-year time period. So then you end up with a cube of longitude, latitude, and time in months, and that might be 240 time steps. Okay, so then we start and we create our monthly mean climatology. So in this case, from the previous step, we are going to take each calendar month. So for instance, all 20 of the Aprils in your time period, and we're going to calculate the mean of those 20 Aprils. And that will give you the monthly mean climatology. And you're going to do that for each of the months. So that means you're going to end up with a per pixel mean over the entire time period for each of the months. And this is one of the climatologies that we're going to be using today. And then the last thing that the NOAA methodology requires is what's known as the monthly mean, the max monthly mean, or MMM climatology. So what this is simply per pixel, it's taking the maximum of your previous monthly mean climatology. So out of those 12 time steps, you're just taking the maximum, and this kind of represents, on average, the maximum expected temperature that you could expect for any specific pixel in that area. Okay, so these are the two specific climatologies that we use to create our data products. Okay, so let's go look at just some of the mapped products that we will be creating today that might tell you give you some information about coral bleaching. So first of all, like I said, you just want to know what the temperature is on any given day. So this is just the sea surface temperature, and it just represents the most recent observed state of the ocean. So what we will be using for this is simply the near real-time austere sea surface temperature product. The next one that we'll create is also a fairly standard product, and this is the sea surface temperature anomaly product. So in this case, it represents the deviation from a long-term mean condition. So for today, all the positive areas are being shown in yellow and red, and this just means that the sea surface temperature is warmer than average, whereas the negative anomalies, which is in a blue to purple color in this case, means that it's cooler than average. And the products that are required to create this is simply the near real-time austere sea surface temperature, and then also the monthly mean sea surface temperature climatology that we created. The next product that gets more into the NOAA methodologies is the sea surface temperature hotspots. Now, if you remember from earlier in the week, anywhere where the temperature is effectively 1 degree warmer than the maximum that the corals usually experience, that is where the coral bleaching risks tend to start. So the hotspots, we're looking at any areas, only positive anomalies that are hotter than the max monthly mean climatology. So it's all the areas that are warmer than the maximum expected temperatures. So in this case, it shows you all of the positive anomalies, but everything that's warmer than 1 degree above that is being shown in yellow because that's where your risk starts. So to be able to create this product, you would require the near real-time austere sea surface temperature and the MMM climatology. And then one of the critical products that shows you the accumulated heat stress over time is what's known as the degree heating weeks product. So this is basically just an accumulation of heat stress conditions. So in other words, it's showing you areas where the hotspots are greater than 1 degree, and it's accumulating this over a window of 12 weeks or 84 days. So basically showing you all the accumulation of the heat over a period of time. So to create this product, you would need 12 weeks or 84 days of sea surface temperature hotspot products. So in other words, 84 days of your normal sea surface temperature and an MMM climatology. This might seem complicated, but we do have all the code to create this product for you, so don't worry. On the NOAA Coral Reef Watch methodology, degree heating weeks over 4 degrees Celsius weeks is where the trouble starts. So that's also why it is noted in yellow. And anything warmer than yellow is obviously even more heat that's been accumulated. So that's even worse. And one of the last products is the bleaching alert areas. So this is showing you the current potential risk of bleaching heat stress. And this uses the degree heating weeks products and the hotspot products to create this map. So it's basically showing you areas where there's no stress or where the hotspots are below 0. Otherwise, if you need to start watching out, it's areas where the hotspot is between 0 and 1. Where you have to start, where it's a bleaching warning is when the hotspot is over 1 and the degree heating weeks is between 0 and 4. Bleaching is likely if there's a hotspot over 1 and the degree heating weeks is between 4 and 8. And then severe bleaching is likely if the hotspot is over 1 and the degree heating weeks is between 8 and 12. You'll also see later on in the practical that they also have included further alerts, so alert 3, 4, and 5, and this just scales up degree heating weeks between 12, 16, 16 to 20, and 20 to 24, I think. But yeah, we can see that later on. And then lastly, what's very useful is to be able to graphically represent this data. So in this case, what I'm showing is the statistics of an area, but you can always just take 1 pixel at a specific reef that you want to monitor. And this is just useful because it's able to give you the historical perspective of either the sea surface temperature information, or you can actually graph out the anomalies or the degree heating weeks or the hotspots. Any of the products that we're creating, we can create a graph for in time as well, and we will be doing that today. Okay, so that is the kind of the theoretical component of today done and dusted. I can now hand back over to Ignatius, and we can start exploring.
Thank you, Marie. Very insightful presentation. Before you go on, there are just a few questions I have for you. So if you can just spare a few moments for me.
Of course.
Okay, so the first one is looking at, what are some of the main limitations of relying on temperature-derived indices alone for reef monitoring? And are there any other complementary indicators that we should consider or we could consider?
Okay, I'm gonna take that from my side, but I would definitely value the input from James and Karen on this one as well. So from the sea surface temperature side, I think we did touch on it yesterday as well, in the sense that the satellite information obviously only gives you the surface of the ocean. So it's always valuable to have at least a good understanding of your entire water column and whether there are significant changes between the depths and the surface temperature. Karen did mention that sometimes the reefs are fairly shallow, so there might not be a big variation. But yeah, so in that sense, that's from the temperature side. Obviously, temperature is not the only thing that can potentially lead to coral bleaching, or at least to the risks of the coral's health. So in that sense, things like monitoring the water turbidity, which is also an ocean color product. So the turbidity, monitoring things like the chlorophyll in the water column, suspended sediments. This might also help to monitor the coral health. Yeah, so these are potentially complementary products that can be used as well. Maybe James or Karen feels like they could add something else to that.
Yeah, so yeah, Mary, that's true. And so from our side and through experience is that also the expert knowledge and expert opinion also counts more. And also knowing the reef locations, because at times you might have uh, like there are alerts showing in areas that there are no reefs, for instance. So in this case, the expert knowledge is also quite important to know. It helps in the issues on the complementing the observation from the set night. But basically saying that temperature is the predominant driver of the bleaching, and this is what from our end we've relied on mostly. It's not quite often that we do document bleaching from other issues like pollution, which is always localized to some extent. So, yeah, just providing some insights around that.
Thanks, James.
Karen, would you want to add anything to it, or can I just move on to the next question?
No, nothing really to add. I think you should move on to the next question. But thank you.
Okay, thank you. The next question has to do with the monitoring frequency and data resolution. So how does the frequency and resolution of the temperature data affect our ability to monitor reef resilience accurately? Are there any minimum requirements or preferred data sets that you can use for effective monitoring?
That's an interesting question, actually. At least when it comes to the temporal resolution, I think, these things, especially like a marine heat wave, I do not think that happens, it doesn't just happen overnight. The heat stress tends to accumulate over time quite gradually. So I think in terms of the daily temporal resolution, it's generally considered to be sufficient. I know originally the Coral Reef Watch products tended to only be updated on a couple of days basis, but nowadays it is also daily. Yeah, I mean, in terms of for instance, the spatial resolution, I do note that the Austere products are about 5 kilometer spatial resolution, so that is potentially not showing you very fine scale variability, but it does show you the synoptic conditions quite nicely. So, if there is a blob of warm water that is heading in your direction, that is always a good warning sign. Even though the spatial resolution might not be to a meter scale or anything like that, you are getting the larger synoptic signals of the temperatures are increasing. It's a problem. So that's it from my side.
Okay, so I think there's a follow-up question or a question that just could be linked to that. So in this case, which satellite missions could be recommended for remotely detecting some of these reefs, apart from maybe the austere level 4 datasets? And what are some of the advantages and disadvantages of using such remotely sensed data?
Are we talking about looking at the reefs directly or monitoring the environmental aspects? I'm just noting that
monitoring the environmental aspects.
Okay, so in that case, I would stick with a like a nice long-term climate quality type of data set. So that is why we have focused on the Austere data product. It's difficult to kind of tailor your methodologies for a short-term mission because it might end in a couple of years' time. So that's where it's very useful to rather focus your methodologies on these types of methods and data sets and missions that are kind of long-term continuous to go ahead. Sorry, that's a very broad question, but I unfortunately don't have all the answers to go into all of the different satellite missions at the moment.
Yeah, that's fine. That's fine. I'm just reading the questions from here. So the next question has to do with, and I think you did mention it a bit, but is there typically a lag between the observed temperature spikes and the bleaching events? And how do these temperature-derived indices also capture or account for this?
I'm going to defer to the experts in the room on this one. So maybe James and Karen can let us know if they're like what the lags are in the bleaching alerts. I think they have a good operational sense of these types of things.
Yeah. So essentially, James, I'll let you add on to this as well. So often what we're looking at is these bleaching alerts based on the degree heating weeks, because at that point we know there would have been heat stress for a prolonged period of time. And some of the variations we tend to see are also species dependent. So we've got either some species of coral that are a little bit more resilient, or particular areas that might have various conditions like upwelling that might create some protections, or conversely, we might see somewhere near the mouth of a river that's also dealing with sediment stress. So it's not always an absolute direct comparison, and you have to really start to consider some other environmental local factors that might be impacting the reef. So again, that's why we use the bleaching alerts to essentially mobilize people to then go out and verify whether we're actually seeing the bleaching as we expect. I'm not sure, James, if you wanted to add anything to that.
Yeah, I think you've captured that, Karen, and so from the in situ observation data that we've received and we continue to receive, so some of this information kind of align with the alerts that we do get from the satellite observations. So for instance, we've tried, and it's unfortunate I don't have an opportunity to share that map now, but you will see all the reports that we've received this year for that were mentioning bleaching observation to some degree. So they were actually they kind of overlay perfectly with hotspot areas and areas where we had accumulation of heat stress, and there are opportunities for people to report data from those areas. So I think it's just a matter of extensive validation, and we can say for sure that there could be some direct correlation in that essence.
Okay, thank you very much, James. There's a question here about the importance of buoys, but I'm not too sure what the question is directed at, but I'm going to rephrase it for you. Do you have a network of buoys, or what is the system like for collecting in situ data around these areas?
So I personally, we don't have specific buoys that we focus on for ocean validation. I mean, when we do, we tend to focus on the optical side of things, so validating things like the remote sensing reflectance. But for instance, the Ostia product, they actually use the in situ data for correcting the bias, if there is any bias, like whether it's only a 0.2 Kelvin, for instance. They would use any in situ information that they can get to correct the bias of any satellite mission. So in that case, they make use of opportunistic buoys, ships, things in the floats in the water at any given time. I'm not sure if any of the key reefs around the Wire region, for instance, might have some permanent temperature sensors moored. That might be an interesting thing to find out from our Kenya team.
Sorry, Mary, but just to jump in quickly on that. So we have some temperature loggers that have been installed by different people, and I think Mike Roberts from Nelson Mandela University some time back did install these loggers, and I also know that the Wildlife Conservation Society, for instance, they have these loggers. So they're just opportunistic installations that maybe we could use, but yeah, they exist, and only that we need to get that information out there from the third-party people.
Cool.
Okay, thank you. It seems Urias came back with his question and he rephrased it this time round. So he's asking if you can detect coral reef structures via satellites, and if yes, which missions have been used for this? Yes,
Okay.
which missions have been used for this?
So far, I know that I think they've used Sentinel-2 and Landsat, but I think it was touched on this week so far that it's generally you can see like the bottom type in the kind of like the larger sense, in the sense of whether it's potentially seagrass or sand or coral, but you might not be able to differentiate between the different types of coral. You might need a higher spatial resolution method for that, for instance, like an underwater vehicle or something with a camera on it or a radiometer on it. But yeah, so definitely Sentinel-2 has been used. I'm not sure if any of the Planet missions have been used, James.
Yeah, I've seen the Khalif bin Sultan, somebody. So they did extensive mapping of corals, but not to the species level, using Landsat imagery. And yeah, of course, the higher the resolution, the spatial resolution, the better, and in that way you can be able to map the reef structure, but not the species.
Yeah.
Okay, thank you very much. I think that is it for this round of questions. So we'll be moving on to the next part of the training, which will be looking at an introduction to the Dunia Sandbox and Jupyter Notebooks. So I'm going to be handling this session for today. It's going to be mainly myself and Marie, but we still have James, Karen. I don't know if Swale is here today, would still be assisting if you still have any questions. So I'm going to move on to the Dunia platform again, and I'd encourage you, if you can, please follow along with the tutorial, and the chat section is open for any comments or questions that you might have. Plus, I introduced you to the Dunia platform already. You can just get access to Dunia by simply just typing dunia.esa.int in your address bar, and that should take you to the Dunia website. And to be able to access the sandbox, you should be logged in to your particular profile. Once you're logged in, you just click on the build menu over here and then click on the sandbox. To get any information on the sandbox, you can just quickly click on read the docs, and you should be able to get into this particular page here that would give you all information on the sandbox. Like I said, on the first day, you have certain allocations to each account. You are getting 16 gig worth of RAM, of memory, 4 CPUs, and about 50 gig worth of storage. If you need any information later after this particular tutorial, you can go to this page and have all the information about the Sandbox and Jupyter Notebooks from this particular page. So back to the section. To launch the Sandbox, you just click on this button here, and then it should redirect you to the Sandbox. So immediately you do that, it's going to load out the Sandbox for you. This does take a while for the first-time users. I have already been using this profile for a while, so everything seems to be already set up for me. So it's going to be pretty fast from my end. And I hope, in case you are having any difficulty logging into the Sandbox, please draw attention in the chat section, and we'll see how we will be able to assist you. So once you log on into the Sandbox, this is your typical screen that you're going to see. So you're going to have the notebook section, which is composed of the Python, the desktop area, as well as some documentation. You also have access to R and VS Code within the Sandbox. You're typically going to land in your root folder, which is going to have all your elements within here. Because I've been using Sandbox on this particular profile, there are certain elements that are going to be in my root folder that you are not going to have. Typically, the material here that you see, I've already transferred into my Sandbox for the purpose of demonstrations this afternoon. But alongside that, you also have some introductory scripts to help you, an introduction to Python. You have an introduction to Earth observation calculations to create certain vegetative indices, and also, most importantly, a script for data access. The first thing that you're going to do to create your notebook is just to click on the Python 3, the IPy kernel over here, and it's going to open a new notebook for you, which doesn't have any name over here. So it's untitled till you begin to save, and then it will assign a name onto it for you. The good thing about Dunia within the Sandbox is that it is also easy to be able to specifically get certain data within the Sandbox. So if you look at the far left over here, there's the EO DAG, which helps you to be able to access data within the Sandbox. So this is more or less like a graphical user interface, which is very easy for you to browse via the map and then select data for specific areas that you're interested in. So for today's example, I'm going to be centering again around Northern Africa in parts of Egypt. So to select your area, you can do that via drawing a polygon, or you can just simply draw a rectangle or a square. So I select and then I click and drag. Once it is released, your area is selected for you. So you have this very cool bounding box within which you are going to search for particular imagery. It's also very important that you highlight or select currently the data provider from here, from Cloudflare. The DIAS that is being used, the data information access system, is the Creo DIAS. So you might want to select that to be able to get better results. Each data set that is being accessed is being accessed through a different DIAS. So you might want to select the Creo DIAS for all the Sentinel missions that you'd be searching for. And then you also have a drop-down menu here that enables you to select the particular data of interest, or if you already know the product name or file type, you can just begin to enter like I'm doing over here. I start with S2, which is representative of Sentinel-2. You can get it in both level 1C or level 2A products. So in this instance, I'm just going to select level 2A for this particular demonstration. You can select a date range. For this particular demonstration, I'm just going to select the entire month of January 2024. And then you're going to also, you can sort of filter out the amount of cloud cover that you want within this particular image. To finish and view the results from this particular query, you just click on preview results, and then it's going to generate, go through the particular area and then bring out all the information for you. So for that particular time period, these are the tiles available for that particular time period. And once you click on the particular tile or the file name, it's going to give you a quick look preview over here at your right, and then also give you information on the metadata. So for this particular product, we are looking at the Sentinel-2A. We have two of those satellites. There's the 2A and then there's the 2B. But this particular imagery is coming from the 2A. It's an MSI instrument that is being used to capture this. You also get information on the cloud cover, and you can already see from here there are lots of streaks and clouds within the imagery. So this is a lot of the information that you're going to get. And most importantly, before I move on also, I'd want to draw your attention to the product identifier image. This is how you are going to be able to retrieve information within the sandbox in case you want to use it within the graphical user interface. Because the sandbox already holds some of the data within the system, at times it is very difficult navigating through individual folders to find a file. So it is easier to just copy the path, and then you can just paste it within your file browser in the graphical user interface to be able to access the files when you are using the graphical user interface. Once you're satisfied with the results, you are able to paste this within a code within your Jupyter notebook. So I'm just going to keep moving along over here for a specific imagery that I feel will be good enough for mine. So this is an image of this particular area with about 5% cloud cover. So I just click on generate code, and then this is going to put a section of the code for you. So every single step that we just took within the graphical user interface, it has generated this into a data query code for you. Very quick and easy. Within the sandbox also, like I said, there is the graphical user interface that is able to connect and then allow you, for those who are not too familiar with the Jupyter notebooks and then Python scripts, to be able to use it like you would use your normal PC with your graphical icons and a desktop. So in this particular graphical user interface, you already have some applications pre-installed in this particular interface where most people are familiar with. So in case you want to use applications like Snap, like QGIS, like Grass, even with R, all these particular applications are already installed in this graphical user interface for you. So you can either navigate to under education, we have Grass, and then we have the QGIS desktop in here, and you should be able to use it like you normally do on your local PCs. The same for Snap. You are able to launch and use Snap also within this particular interface. You're able to load the data directly from Dunia into Snap without the hassle of downloading the data and having to re-upload the data into Snap for you to be able to use it. So like I said, instead of navigating to individual folders, every single data available on Dunia is within the EO data folder. So if you look into the EO data folder, you're going to have a list of data sets from JSON, Landsat, Sentinel-1, Sentinel-6, Sentinel-2 within here. But it's going to be a very cumbersome process, especially not even knowing the particular tile that you are interested in and want to download. So with the file path already in your mind from the query that you just did, you can easily just paste this within the dialog box you see here, and then you should be able to open this inside Snap in this graphical user interface. I'm going to go back to this particular documentation. Most importantly, also within the sandbox, there are already some pre-configured notebooks that you can use and also be able to tweak for your particular area of interest and also for your applications. So to get these sample notebooks, you just come to the wiki on the sandbox and then you click get example notebooks. So what this does is that this is within a Git repository and it's going to clone this repository into your particular account within the Dunia sandbox for you. So once this is cloned within your repository, you should be able to see the sample notebooks also within your workspace. So these are just examples of some of these notebooks in here. And then once you click on it, it should be able to load. Luckily, these notebooks come with a lot of details and step-by-step explanations about what is being done at each level. So they are very easy to follow and they have very detailed instructions about how they should use it. Again, people tend to ask, do I need to have a background in Python? Do I need to know every single thing? To use Dunia, I would say no. It depends on what you want to do because this is so structured and it has so much information on how every particular step is well explained within this. All you need to do is have the ability to read and follow instructions, and you should be okay. So these are just examples of notebooks to be able to plot this particular product. So it's either a wave product or a current product for the Gulf of Guinea area in West Africa. There are several examples of these notebooks also for floods, for coral bloom monitoring, as well as other applications. For today, we'll be looking particularly about looking at how we can use these Jupyter notebooks to assess coral bleaching events. So this will be handled by Marie, and not wanting to jump too much into that, I'd like to pause here and take some questions. And from that, maybe Marie can take over and we look at this particular sample notebook. Oh, sorry. I just realized that someone says I was going a bit too fast. But don't worry, the recordings will be shared with you at the end of the training, all 3 days, and then you would be able to go along with it at your own pace. But we're hoping that Marie talks a bit slower than I do, so she will take it very slowly, step by step, and you should be able to follow with the tutorial. What I'm doing right now is just giving you an overview. So thank you very much. If there are any questions, I'll take them now. If not, I'd invite Marie and then we can go through the particular Jupyter notebook for this particular session.
Are there any questions?
Marie, I see you're sharing your screen already.
Is there anything in the Q&A? Sorry, I can't see the Q&A. Okay, if not, I'm going to take it from, can we download Sentinel-2 from here to our laptop or drive? I think you should be able to download the Sentinel-2 data once you've opened it. Basically, anything that's showing on the left-hand side here, so in your file structure, you can click on any of these, right-click on any of them, and you should be able to download the scripts or the data sets. So if you see anything on the left-hand side file viewer, you should be able to download. Similarly to that, there is also the option in Dunia to upload data. So if you look at the top next to the big blue plus button, there's a little folder, so you can add a new folder, or you can upload files. So if you click on that, it opens up your personal directories on your personal PC, and you can then select any file that you can upload. So in your Dunia notebook, correct me if I'm wrong, I think you've got about 10 gigabytes worth of space. And then you've also got an additional probably up to 50 gigabytes of space on your virtual machine. So there are a wide variety of areas where you can store data on here. But yeah, for instance, it's nice to upload some shape files or something like that if you want to use that to crop your data of interest. Okay, so let's start off with getting you guys some data. So what we're going to do is we've shared a Git repository with you. Perhaps, Ignatius, if you would be so kind, oh, actually, I can do that because I have it open here. I'm just going to post it in the chat. The link to the Git repository. So this is just an online location where we have shared all of the code and also some of the NetCDF climatologies that we're going to be using today. So that is in this coral bleaching monitoring repository. If you click on the link that I've just posted in the chat, or which Ignatius shared in an email with you earlier today. So what we're going to do is on a Git repository, there is on the right-hand side, you've got this green code button. And if you press on that, it brings a drop-down menu. And that gives you the location of this specific repository. So we want to go to, there's a different HTTPS, SSH, and a GitHub CLI. So we want to be on the HTTPS tab. And we want to copy over this Git repository. So you can just press the little 2 boxes to copy the URL to your clipboard. Okay, so this is the link to the Git repository. So we're going to copy that, and we're going to go back to our Jupyter Lab environment in the sandbox, and we are going to clone our repository. So to do that, there is a Git drop-down menu at the top. So next to File, Edit, View, Run, Kernel, Git. We press on that and we select the second one from the top, which is the Clone a Repository button. That gives us the option to enter the URI for the remote Git repository. So I'm just going to copy that, copy paste. So I use Control V to paste that. And we're going to say include the submodules and also download the repository. So, sorry, I wanted to just say before you do that, you want to make sure that you're in your root folder. Otherwise, if you are in one of the other folders, then you're going to clone your repository in there, which is not a problem. It's just nice to clone all your repositories in your root folder. So do you make sure that you are in, you only have this little one folder showing at the top here. So I'm going to go back, say git, clone a repository, copy paste my repository, download all the repository, include the submodules. So select both of those and you say clone. And it's successfully cloned. So now you should have a folder within your root repository that says coral bleaching monitoring. Okay, you can go into that. And now you should see that the entire bunch of NetCDF files that you need, your Python code that you need, and the 3 Jupyter notebooks that are in this repository, everything has been cloned into this. Okay, now the next thing that we are going to do is we're going to start looking through the notebooks. So the first one that you have is this 00 Copernicus data download notebook. Okay, so you can double click on that and then it'll open up on the right hand side for you. Okay, so the nice thing about Jupyter Notebooks is that it's a very interactive environment and it's also a very informative environment. So the notebooks contain what is called markdown cells. So anything that looks like the text that you might have in a Word document, that is the markdown cells. So this is basically, if you double click on it, it just shows you that it's using the markdown format, and it's just a rich way of writing the text. Okay, so anything that is markdown cells is not actually going to execute. So you can see here, the markdown cells are all a very white color, and then you have this slightly grayer color cell with little brackets next to it. And this is, if you click on that, you'll see at the top here, it's changed to code. So anything above that, here it says markdown, and below that it says code. So that means that this cell is, if you're going to execute this script, this is one of the cells that's actually going to execute code. Okay, so the other thing to know is if you want to go through and run cells, so you'll hear us say that a lot, you want to run a cell. If you look on the left-hand side here, you can see these little brackets are empty. So this means that this cell has not yet executed. You haven't asked basically Python to do anything yet, to execute any programming yet. Okay, so to be able to run a cell or to execute a cell, you first want to highlight it. So you just click on it. So anywhere that you highlight or anywhere that you click, a little blue section appears on the left-hand side. So for instance, I want to execute this cell, and then I'm going to go to the top where it says, where there's a little play button. You can either execute it by pressing that button, or you can go to the drop-down menus where it says run, and you can say run selected cells. Okay, so what that's going to do is actually execute the code. And once it's busy executing, a little star appears on the side here. If you're doing a very complicated execution, it might take a while to actually run. But this one is fairly straightforward. It's just importing a bunch of modules. So that one just takes, just goes very quickly. And now it says 1. So that is the first cell that you've executed. As you move down the code, all of this is marked down. So none of this is actually going to execute. So you can just press the play button and move through everything. So it's just going to go past it and not actually execute anything until you get to the point where there's another code cell. Okay, so this specific script or this specific notebook that we have given you is to be able to download data from the Copernicus Marine Services. So if you remember yesterday, I showed you there's a little, when you go and subset the data, there's a little automate button, and it gives you this little box of code, which is effectively giving you the same variables that you've selected earlier. So in this case, we are telling Copernicus to fetch this specific data set, so the Austria near real-time data set. So that's the data set ID. You're telling it to fetch the sea surface, to analyze sea surface temperature data. You're giving it a bounding box, and you're also telling it which longitudes and latitudes to go and collect. Okay. So unfortunately for us, the Copernicus Marine Services have been having some issues since yesterday, basically. So unfortunately, I don't think this script is going to run right now. So I'm just going to try it. At least the first part starts nicely. So it gives us the option to input our Copernicus username. You press enter, and then it asks you for your password. So I will quickly grab my password, and hopefully that will just work. Okay, so this is where it's useful to have a short, easy password to input. Okay, so if this works, a little box at the bottom will appear here, and it'll ask you if you'd like to confirm the download, and then you press yes or Y when you're prompted, and enter, and then it'll actually download this subset that you're asking it for into the current folder that you're in. Unfortunately for us, CMEMS is not working with the login currently, so that is not going to happen. So Ignatius has kindly shared with us a Google Drive link to the download that would have appeared here. So what you can do in your free time, or in either now or as when you go over this code again, is to download that netcdf file to your personal computer and then to upload it into this folder on Junior. Okay, so it's important to note that once you start uploading the data to this folder, the name will appear in the folder almost immediately, but it will not be completely uploaded for a couple of minutes. So there will be a little bar at the bottom here saying uploading, and it'll show you the status of your upload, but you will not be able to actually use that file until the upload is complete. So please keep that in mind if you're trying your scripts. It's not actually going to work until that upload is complete. Okay. Yes. Okay. So this means what you're seeing here, unfortunately, is that the credentials aren't currently working. So hopefully by the end of this afternoon or by early tomorrow morning, CMEMS would have sorted out its problems and you will be able to download this in this way, because this is a very nice way to actually download the data. The thing is that you can change the dataset ID to any of the CMEMS products. You can change the variables, you can change your dates. So this is a very useful way to be able to download the data directly to Junior. So you don't have to go through the process of putting it on your local PC and then uploading it to Junior. Okay. One more thing that I wanted to show is in your personal Junior environment, you might not always have all of your packages, all of your Python packages is installed from the get-go. So if you, for instance, run this script for the first time, you might get an error that says the Copernicus Marine Toolbox has not been downloaded yet. So in that case, you can simply run this line of code that says pip install and then whatever the package name is. So in this case, we're asking it to install the Copernicus Marine package and the X-Array package. You can simply ask it to install whatever package it says you don't have, if that is the case. How Junior works is once you've installed that package, it should usually just be available on your environment in future. So you shouldn't have to install it several times in a row. Okay. Another thing to note about notebooks or working in Python in general is that anytime there is a hash in front of a line, that line is not going to execute. So in this case, it's just giving you a little bit of extra information. So for instance, if you have this line of code here and you don't want it to execute next time, you can simply put a hash there. Okay, so you'll see in the other scripts, there is this line of code as well, and you can either delete the hash or add the hash as you need it. Otherwise, once all your packages are installed, everything should be able to run. Okay, so this notebook specifically is only for getting the data. So I'm going to close it because we're not going to need it again if you are getting the data from the Google Drive or if you've already got the data somewhere else. Okay. I'm just going to discard the changes. Okay, so you guys can carry on working in this folder. I am going to move to the folder where I do actually have the, the data set in. Okay, so next up, we're going to load the notebook called 01 CBM Coral Bleaching Monitoring Product Maps. So double click on that one and it'll load up the notebook for you. Okay. So this notebook specifically is going to use the austere data sets that we've got. And we are going to read in the data products and we're going to plot the different products that I showed earlier today. So we're going to be mapping out the sea surface temperature, the anomalies, and all of those things. Okay, so let's just look a little bit at the code. Here we've got a table of content. So it's going to tell you a bit about the data set. It's going to tell you about loading your required Python modules. It's going to load the data sets. You're going to plot the climatology data. You're going to derive the indices, and you're going to derive the degree heating weeks and the bleaching alerts. Okay, so this just tells you a little bit about Coral Reef Watch. Here is a link to Coral Reef Watch if you'd like to go check it out. Okay. And this also just gives you a little overview of the area that we're working with. So we're looking at the Red Sea, and we're looking at the time period between the 1st of January 2023 and the 1st of September 2024. Yeah, as I mentioned many times this week, we're using the Ostia sea surface
Marie?
temperature product. Yes, sorry. Hello?
Before we proceed, I just wanted to ask the audience if they're, because I'm receiving a few feedback, a little bit of feedback in the comment section, and I just wanted to know if everybody was okay so far before we move to the visualization.
Cool.
Yeah, okay. I'm getting a thumbs up, so I think you can proceed.
Okay, cool. Okay, so everyone will be using the Ostia product. This is a level 4 product from the Copernicus Marine Services. There's links to the product user manual and the quality information documents if you would like to check it out. Here it's just telling you about the options to get to the data. As I mentioned, we are going to use the method of in this case, unfortunately, probably downloading it from a Google Drive and then uploading it. But hopefully, eventually, you'll be able to use your Copernicus download script to get the data set. Okay. And next up, so the first thing when one runs a Python script is that you actually have to import all of the different functionalities that you want to use. So for instance, NumPy is your mathematical functions. So you want to tell Python, I'm going to be using the NumPy package. You want to use Xarray because that works very nicely with netcdf files. Matplotlib is a very nice plotting package, and CartoPy is great for using geospatial data and displaying it on a map with coordinates. So basically, this first cell is just telling you is just showing you how all of the packages that you need to install. So if you're running this cell for the first time, so for instance, if we press the play button, like I mentioned before, many of you might find that there is a little red box that appears at the bottom, and you might have a module not found error. Okay, so all this means is you need to pip install and whatever modules are missing. So we've created this little second box. So you can just click on it, remove the hash at the front, and then you can run this box on its own. And that should hopefully install all of the missing packages that you might not have on your first run. So in my case, I already have these, so it's not going to install everything. It's just going to say the requirement is already met. But for you, if you don't have the package, it will actually install the package. So I'm going to hash this out again because I do not specifically need any of these. And if you want all of this to go away below, once you've hashed it out, if you press play again, it'll just take everything away, which is quite nice. So you don't have to scroll so far down. Okay. So what you might find in your code, particularly the ones you've got from that you've cloned, is that there's already a number that's appearing on the next to all the code cells. So that means that the notebook has already been pre-run. So in a sense, for training, that is quite nice because you can see what the output for each of the cells is supposed to be before you try and run it. So if anything is wrong with your cells, or sorry, with your data, if you don't have your data set yet, you can still see what each of the outputs were supposed to be. So for instance, in this one, we are plotting the monthly climatology data. So you can see what the plots are supposed to look like. And then once you go through the notebook and you plot it yourself, this will be recreated if all of your data are actually there. Okay, but sorry, let's go back and actually just run through all of the codes bits by themselves. Okay, so this cell, we're going to be loading the data product. So we are calling X-array and we are loading our data file that we either downloaded from Google Drive or downloaded from the Copernicus Marine Services. It's actually quite nice because it shows you the extent and it also shows you the dates that it downloaded. So it's quite a long file name, but it's very useful. Okay, so it loads that data set and it also loads your climatology data. So the climatology data are these two netcdf files, and they were, you got them from the cloning. So they were quite small files and they came together with the data and the code. So you didn't have to specifically download them from Siemens. Okay, so if you run this, it should work. I do see that someone has received a load product giving you errors. I think there is a possibility that, for instance, if your upload hasn't completed yet, if your internet connection is not very fast, the upload might still be busy. So in that case, it will probably give you an error. So once your upload is complete, hopefully that should be fine. The other thing you can do is you can also look at whether this Met Office, you can see the file name here. If that file name is exactly the same as the file name that you have over here, because if it is not, then you can maybe just copy, if for some reason we accidentally gave you a slightly different file name than the one. I really hope we didn't, but if that is the case, you can use, you can go to rename and just copy that file name into here and just rename your file to whatever the file is that you copied. I'm just going to look quickly at the error.
So Marie, maybe just to comment also, maybe also when they were downloading, you should keep the file name intact. And if you change it, that has to reflect again on the code that is calling it. So probably I've seen the file that Ignatius shared, so it is the same name. So probably somebody might have changed the name when they were downloading.
Yes, this is true. So basically, whatever the netcdf file, the 100 megabyte netcdf file that you downloaded from us, or whatever the file name is, please make sure that this file name is the same. So you can either rename your file name to this, or you can change this bit of text to whatever your file name is. Okay, so once that happens, it should hopefully work. So for now, I'm hopefully going to carry on and everybody can, we can troubleshoot again a little bit later. So for instance, we're going to look at, if we just say, so we've loaded in the variable as, or sorry, the data set as data. So if you just run data on its own, it'll show you what the format is of this data set. So for instance, you've got 610 time steps. It runs from where we said it would run from. You can see the longitude steps, the latitude steps, and that it is analyzed sea surface temperature. So it's opened up a data cube for us with time, latitude, and longitude. Okay. So let's actually start plotting some of the data. So we're first going to look at, like I said, we're going to look at the climatology. So this is the data that we actually provided for you. And this is a monthly climatology between 1995 and 2015. Okay, so it is that the Red Sea sorry, the Red Sea SST mean climatology that we are looking at. So first, if we just run this cell, it should plot it out for us. Okay, so in this case, the bluer temperatures are cooler, the warmer temperatures are redder. So you can see that generally the beginning of the year has got cooler temperatures overall, cooler also in the north of the Red Sea. And then September seems to be the month that is the warmest. September and October, sorry, not October, August seems to be the months that are warmest overall over the Red Sea. Okay, so that is just the plotting the normal climatology. And then we can also plot the monthly climatology. So that is this Red Sea max monthly mean climatology. And as I said, that's just the one time step. And that is only representing the warmest pixel of the mean monthly climatology for the whole area. Okay, so you can see that it looks very similar to September and August in the image above, because it's basically just representing the highest number, the highest temperature from each of those images. Okay, so then we can start looking at the sea surface temperature climatologies. In this case, you can select any date within the time period that we have. As I mentioned here, remember that you need 12 weeks of data to be able to calculate the degree heating weeks product. So I suggest you choose a date anywhere between the 1st of April and the end of the time series. So you still have at least 3 months to use to create your degree heating week product. Okay, so in this case, I chose something in the warmest period so that we can see what those products were looking like. So as the target date, you can select any of the dates within this time period, I would suggest. But let's stick with the 30th of August for now. You can always change it on your next run. Okay, so first of all, let's just make sure I run all of this. First of all, we are selecting the date. We're opening our sea surface temperature array. And in this step, we are getting the daily climatology. So the daily climatology is effectively an interpolation of the monthly climatology data. So it takes a linear interpolation between the 15th day of each month. So for instance, if you are looking at the 1st of December, it'll linearly interpolate between the December climatology and the January climate. If you're looking at the 1st of December, it'll look at the November climatology and the December climatology. That all sounds very complicated, but there is actually a little Python script that you've imported here, and it's just making use of that to calculate the climatology. You can open up that Python script and look at exactly what it does, but luckily you don't have to actually understand it because it just magically does it for you, which is the great thing about Python. So here you're calculating the exact climatology for whatever date you selected. Okay. Once again, you're calculating the anomaly. So that is your temperature today minus your climatology mean for that specific day. So, okay, let's just make sure I've run everything. I'm going to run this one again just to make sure. We're going to calculate our hotspots. So our hotspots are making use of your sea surface temperature array, and you're using your max or your MMM climatology in this case. So sea surface temperature minus max climatology. And your hotspots are anywhere where the climatology is positive. So you're only looking at the positive anomalies in terms of the hotspot. We run that one. And then we're going to actually start plotting the data. So this, as I mentioned, we have the cartopy function. So we're giving cartopy a projection. In our case, the projection is not that important, but when it comes to plotting things like the South Pole or the North Pole, it's very useful to have different projections to use. Otherwise, the plate Curie projection is usually, this one is usually appropriate for many places around the world. So we're also going to use some of the cartopy functionality. We're going to add some rivers. We're going to add some coastlines. So you can see these data at the top here. This was only plotting just the sea surface temperature data, and everywhere where there wasn't data, it just made white. So in our next plots, we're actually going to assign some, assign some coastlines and things to add to the plots. Okay, so this, the first time you run this section, it might take a while because it's going to try and fetch all the natural earth features and all of the coastline features and all of that from the internet. So it might take a little while for this plot to be created at first. Mine is fairly quick because it's I've already downloaded all of that. Okay, so let's go look at this. If we look at the code, where we're actually plotting, it's this slide. So we are plotting the latitude, longitude, and the sea surface temperature array. And the thing to note is that the Ostia data comes as Kelvin. So in this line, or this little bit of code, we are just converting the Kelvin to degrees Celsius. So the first image, this is the image on the left, is just your sea surface temperature. And then the other one is your daily climatology data. So that is the image on the right. So basically, climatologically, on the 30th of August, this is what your expected temperature is, effectively historically. And this is what the temperature was on the 30th of August 2024. So you can see that the temperature overall was fairly a lot warmer than it usually is at that time of year. Okay, so this is just showing you the temperature climatology and the actual temperature. In the next figure, we are going to plot the anomaly. So where it's warmer or cooler than usual, and we're also going to plot the hotspots. So let's run that one. Okay, so this one gives you, you can see the axis has changed. You can see the cooler temperatures as blue. You can see the warmer temperatures as red. So everywhere where it's red is where it's warmer than historic, where it's warmer than average. The right-hand side is the hotspots. Hotspots are only showing positive anomalies. So basically anywhere where it's purple is where it's warmer than 1, and that's where potentially bleaching could start happening. So you can see all the areas where so this is showing where it's warmer than the maximum mean climatology. Okay, in the next section is where we start to calculate the degree heating weeks. So this actually takes your 84 days before the date that you chose, and it calculates the hotspots, and it adds up all the areas where the hotspots were warmer than 1. And that gives you the total, and you divide that by 7 to get the degree heating weeks. Otherwise, it's giving you all of the days of data. So the NOAA Coral Reef Watch methodology requires you to divide that by 7 to get the degree heating weeks. Okay. So once again, luckily the methodology has been made a lot easier just by some predetermined Python code. And it also doesn't even take very long to run, which is nice. Okay. Here I just copied and pasted the NOAA Coral Reef Watch definition for the bleaching alert areas. As I mentioned, originally we only had alerts up to level 2, but now the alerts go all the way up to level 5, which is when the degree heating weeks is equal to or greater than 20 and the hotspots is equal to or greater than 1. And this is like risk of near complete mortality, so more than 80% of corals. So that's quite hectic. Below here, you can see it's just effectively assigning a number to each of these different alert levels. So hotspots higher than 1, degree heating weeks between 60 and 20. And it's just assigning a value, and you can use that value then to plot your data. Okay, so this one, like I said, it's just plotting your degree heating weeks, and it's plotting your bleaching alert area according to what we had calculated above. Okay, so you can see here, the degree heating weeks in the north actually goes up almost to about 20 degree heating weeks, which is at the top end of the warnings. And in this image, you can see the bleaching alert areas, and there were actually some really high bleaching alert levels that occurred in the Red Sea for this period. Okay. Yeah, so maybe we can see if there's any questions at this point. Otherwise, like I said, feel free to go back and change the date to a different target date, and you can see how everything changes. Once you have changed the date, please remember that you actually have to then rerun everything below that point to make sure that it actually takes effect. So if we change this to the 1st of April, you have to go and run everything again after that to make sure that you actually calculate everything for the 4th of April. Are there any questions so far?
I think generally it was on the pace, but so far it's been fine. We've reassured all participants that we will be sharing the recordings with them. But also, if they have any questions, today is the last day. Please get your questions in. And we still have a bit of time, so I can even allow your microphones if you want to talk and pose your questions directly to Marie. So if you have any questions, just type them in the chat or Q&A, or just raise your hand and I'll enable the microphone for you. But for now, I think it's all good, Marie, so you can proceed.
Okay. So just for an example, I changed the date now to the 1st of April, and you can see that the temperatures are a lot cooler and they're actually a lot more kind of in the normal range of what the climatology is supposed to be. And for instance, everything is a little bit warmer than usual, but it's not really warmer than the absolute maximum. So you do not have any hotspots occurring in the 1st of April. You don't have any, there's no degree heating weeks, there's no bleaching alerts. So, you know, the Red Sea is not always in danger, luckily. Okay, so that is the mapping script. So after the mapping script, we can move on to the product time series. So this is to be able to plot little time series of the specific locations. So the script looks very similar. It gives you a table of contents. It gives you some introduction. It shows you the data set, shows you what you're using. But please remember that if you've opened a new script, you've effectively starting all over again. So you have to go and import, basically run the script from the top every time. So you need to go and import your modules. You need to go and import your data set and everything. Hopefully you won't have any install errors because you've already installed the packages. So this time you should just be able to skip over those without any errors. So once again, we are loading in the same data set. We're loading in the same climatologies. The data is still the same. But this time we are looking at a specific time period. So we are going to choose the entire range of time from the 1st of April 2023 to the 1st of April 2024. You can choose a longer period, but I do recommend you don't start before the 1st of April, or basically you just want to make sure you've got 12 weeks of data available before the date that you choose so that you can calculate your degree heating weeks in this case. So I have selected 4 locations. We're looking at 4 different places around the Red Sea. These are some stations where there are virtual stations in the Coral Reef Watch catalog. So James suggested that we take a look at these. They are situated all around the Red Sea. So they should show a couple of different kind of situations or values for them. So we're going to look at a year. We're going to look at these sites. And then basically we are going to calculate all of the different things that we just did in the previous one. We're just going to calculate it over the entire year at a specific location. So we're giving it a start date, and we are calculating for that start date, we are to the end date, we are calculating the sea surface temperature, we are calculating the anomaly, we are calculating the hotspots, and the degree heating weeks, and the everything. I'm not sure if I said this, but this can take a few minutes. I think it can take up to about 2 minutes to calculate because it is running over a fair amount of time. So please be patient. You'll see that there is a little star that occurs on the left-hand side. If you go look at the top right, there's a little kernel information on your notebook, and that'll tell you the elapsed time, and it'll show you that your kernel is still busy. So once that is finished, usually the little circle turns clear, and it'll say that it's not busy anymore, basically. So once this is finished, we can carry on to the next step. So after you've actually calculated everything, you can go and plot your time series data. Okay, so I've actually plotted these out already, so we can actually see what they look like. Okay, so in this case, I'm only plotting site 1 and site 3. If you do want to change that, you can basically just change your site long and site lat. So you can change that to site 2. Basically, if you just go look at the top, what we call them, so basically each of them, if you want to rather look at Sudan, you can use site 4. So yeah, you can just change the lat and the long of each of these to whatever you want to plot. In this case, maybe site 4, so you can just change the legend over here, and you can change the long and the lat. So let's just go back to 3, so you guys have the same as me. Okay, so you can see site 3, which is, sorry, just going to go back. Site 3 is Al Madina, and site 1 is the Gulf of Suez. So site 3 is generally a lot warmer throughout the year than site 1. The anomalies are surprisingly not that different. A couple more spikes for site 3, for instance, over time. So remember, here is your 0 is where your positive anomaly starts. So everything above that is warmer than you average. So only in kind of May was everything a little bit cooler than usual. Otherwise, it was all positive. On the hotspots, you can also see when everything was warmer than the maximum, kind of the maximum monthly mean. So remember, it's only positive stuff, so everything else is going to be 0. So you can see where the warmer periods were. And remember, everything above 1, a hotspot of 1 is kind of where the risk starts. So if you draw an imaginary line at the 1, these are the periods that are a problem. Your degree heating week. So this is kind of aligns with your areas where there's where your hotspots are, except it's a little bit delayed because it builds up all the heat over time. As you can see, luckily site 1 didn't go very high, but site 3 did go up to almost 12. And your bleaching alert levels, you can see that site 1 only reached the alert level of 2, whereas site 3 went all the way up to 4. Okay, so once again, you can change if you want to see a longer or a shorter period. If you want to zoom in specifically on the summer period, you can go and change up at the top. You can change this to be whatever date you want. Also, if once again you are interested in completely different years or a longer time period, you can actually go and download a longer time period of data with your Copernicus data download, or physically download it yourself with using the GUI from the Copernicus Marine Services once it's working again. And then whatever you do, all you have to do is change your file name. Basically, make sure that your file is uploaded into your working directory. And you also want to just change whatever the file name is that you downloaded. You want to change this line where you're actually loading your file. You want to change that to whatever your file name is. Your climatologies will stay the same unless you want to look at a different area. But yeah, otherwise, feel free to change, play with this. If you want to make any major changes to the script, I suggest maybe saving a new copy. So for instance, if you right click on your script, you can copy or duplicate it. Or for instance, you can press file on the script that's active. You can say file, save notebook as, and name it something else. So then you've still got your original, but you can also you can go back to the original if you mess anything up. Or you can, and then you can work with whatever else you've done in this notebook. If all else fails, you can always just delete everything and clone the repository again. So that's kind of it for the for the notebooks and playing in Junior for now. I don't know, Ignatius, did you have anything to add, or is there any questions we can answer?
I think so far it's been good. I think there's a question concerning the generation of the anomalies. And so there's a question about, does -4 and 4 correspond to -4 and 4 degrees surface temperature? So if you can just explain how you got the SST anomalies, I think she sort of
Okay.
lost it from that end.
So
Yeah.
yes, the sorry, -degree surface temperature. Yes, it does. So I don't know if I specifically, yeah, I mean, 1 degree Kelvin is the same as 1 degree Celsius. So if you're, and we are keeping, in our case, we do keep the climatologies in Kelvin, and we keep the sea surface temperature in Kelvin until we actually want to display it as degrees Celsius. So it's basically just showing you, it might be showing you in Kelvin the degrees anomaly, but it's effectively the same for sea surface temperature in degrees Celsius. But yes, anywhere where it's red or if it's positive, it means it is, for instance, 1.5 degrees Celsius warmer than usual, than the average climatology for that day. What impact will these have on the corals? Okay, so generally, the overall anomaly is not used in the calculation, so we usually use the max climatology to calculate things like the hotspots and the degree heating weeks. But those are, they generally show very similar patterns. So if you've got a positive anomaly in your normal sea surface temperature anomaly and a positive hotspot, they'll usually overlap a fair amount. The hotspot might just show slightly lower values. But then, so it's basically positive anomalies over 1 degree Celsius is usually what causes the trouble. So specifically, if it's 1 degree warmer than the maximum monthly climatology, then it's going to start causing problems for the corals. And if it stays warmer than 1 degree for a long time, then it accumulates the heat, and that's where the degree heating weeks also come in. So that's where the risk of bleaching becomes more likely. Did we have any other questions? Any other concerns?
Okay, I think that's the only question for now. I can open up the microphones also if we have any questions from participants. You can just raise your hand and then I'll open up your microphone and then you can pose your question to Marie. If you also have any general feedback or any concerns, you can make this also available in the chat or just raise your hand and then I'll open up my for you to address your concerns. Again, I'd like to remind you that all the recordings will be shared with you at the end of the training via email, and it's going to contain also some extra materials and also like a tutorial, more or less. Everything is in the Jupyter notebooks in Dunia, but in case you still have some reservations, you can always refer to the recordings at the end of the training. Please, I'd also entreat you to complete the feedback form and let us know what you think and what trainings also you'd want us to conduct next for your participation. Time is now. If you have any other questions, please just raise your hand and I'll unmute you. Okay, I think we don't have any questions. So I'd like to thank oh, there it comes. Oh, it's just showing appreciation. I'd like to thank our trainers very much. Oh, goodness. Okay. Okay, is that Maureen? Please go ahead, Maureen. Maureen, your microphone has been activated in case you wanted to say something. Okay, I guess that was a mistake. So I'd like to thank all our trainers, to begin with Dr. Marie Smith, Swale, Dr. Karen Moyes, and James Mbugwa for taking time off their busy schedules to be able to participate in this training sessions. For 3 days, it's not easy to get some of these people out of their schedules for 3 days continuously, 2 hours every day. And there's been a lot of preparation also in the background to be able to deliver this training. Honestly, preparations for this particular training started all the way in May, I think. And we've now been able to pull this off. So I'd like to say once again, a very big thank you for all our presenters over the course of the 3 days. I'd like to give each presenter just 1 minute for their general comments on the training. So I'd start with Dr. Marie Smith, just 1 minute. So we can make it brief. Your general observations during the training and comments.
Thank you, Ignatius. I just want to also thank Ignatius for all of his hard work in the background for organizing everything. It's definitely, there's a lot more going on in the background than one realizes. So thank you very much for that. In terms of this week, it's been really great. It's been a really good combination of the background material of understanding the coral reefs of the ecosystem, and also the practical experience of the satellite data. So I think it's been really nice to see how all of that fits together. And yeah, I just want to say thank you very much to everybody that gave their time to come learn with us and to come to experience this this training with us. Thank you very much.
Thank you very much, Marie. Would move to Dr. Karen Moyes. If you're there, just a brief summary, your overall feedback on the training also.
Yeah, I'll keep it very brief. So yeah, firstly, I want to thank you, Ignatius. You've done a fantastic job of running a very smooth training webinar. I'd like to thank all the participants for coming. I know it's also a lot of your time, a couple hours, 3 days in a row. So thank you so much. I've really enjoyed myself. So I want to thank you for letting me be a part of this training as well. And I think it was a really good opportunity to bring some of that, ecological understanding and background and marrying it with all the things that we're able to do with the satellite data to continue to bolster our marine conservation efforts. So I'm grateful to you all for attending and learning some new skills, potentially learning more about the corals that you're using the satellite data with. And yeah, I'd just like to thank you all again, and I really do hope you've learned something and enjoyed yourselves. Thank you.
Okay, James.
So also from my end, it's quite brief, and mine is to thank you all, especially the team. That's Swale, Karin, Ignatius, and Marie for making this webinar happen. And so it was quite insightful. And also to the participant, I appreciate everyone's attention and also the engagement that you've had all along. It's quite encouraging to see that we've sustained the participants all the 3 days from the beginning to the end. So meaning that it has been quite insightful, and it's encouraging to see that. So in all, I think mine is just to appreciate you all and all the efforts, and I hope that we will sustain this momentum moving forward. Thank you all, and enjoy the rest of your day.
And last but not the least, Swale.
Yeah, thanks again. And maybe first, thank you, Ignatius and Mary Smith, specifically for bringing us together with James and Karin in this training session. And also thank for all participants for your attendance, specifically for those who were able to attend all along the 3 days of the training. So generally, despite that, I've been a presenter or a trainer, but my background is ecology. So also I was kind of participant, also learning more from Mary Smith and Ignatius on the other side of a professional, which is also a kind of a very important session for me, which I learned, and I'll follow up with Maria and Ignatius on that part. So I don't have much to add on to that. I think much have been said. Just to say again, thank you, everyone. And this is not the end. Our emails are open. We can follow up for any further question or discussions. Thank you.
Okay, thank you very much, Wale. And before we go, I think Urias missed the picture on the first day. So he subtly gave me a hint by turning his camera on. So if I can please get all your cameras on, I'd want to take a final screenshot for our reporting. If you can all just turn on your cameras so I can just quickly capture this.
James is all blue today.
Wondering what's happening because I don't see any cameras from our participants turning on. Okay. We're having a few coming on now.
They're on the other pages as well.
Yeah.
Thanks for turning your
So
cameras on, everybody.
You've got 10 seconds if you want to appear in the photo. So the time is now. Okay. Just a few more, please. So much, everybody. It's been a wonderful week, and we hope to catch you on again in our next set of trainings. Please expect the recordings and all the materials from this week in an email from me once the recordings are ready. And please, please, please do not forget to fill in the feedback from the training. We'd want to hear from you and also know how we can improve our trainings, our upcoming trainings in the future. Thank you so much for joining us and have a wonderful rest of the week.
Thanks, everyone.
Thanks, everyone.
All right. Bye.
Bye.